Now we come to a new idea. That's called superposition coding. But before we come to superposition coding, I will show you a special case of a broadcast channel here. The reason is that it turns out that superposition coding gives the best possible rate for this channel, this kind of channel. This is called the degraded broadcast channel. You see, the channel is different like the broadcast channel we have before. First, we have the channel from X to Y1, and Y1 goes to decoder 1 and he makes some decision. And after this channel, there's another channel which goes from Y1 to Y2, and then Y2 makes a decision of the common message and the dedicated message for them. And that's the reason why it's called the degraded one, because it's degraded in this way that it first goes to decoder 1 and then it goes to decoder 2. This is called the physical degraded broadcast channel. Later we will see that there is also small generalization of this, which is called the stochastical degraded broadcast channel. And it will turn out that the capacity for both, or the capacity region for both, is the same, and superposition for both gives the optimal capacity region. But now, what is superposition coding? Superposition coding is a method for stacking codebooks. Let's look at the following picture. So the idea is somehow, first, for simplicity, first we assume now that there's no second dedicated message. We only assume there's one common message for decoder 1 and decoder 2, and one dedicated message for decoder 1. I will give some comments how we can generalize this if R2 have also positive capacity. The idea is now the following. First, we have a codebook for the common message. That this codebook here, we generalize it via the alphabet U to the N again, and we use some random coding here, and then the sender gets the common message, he chooses the codebook. And the special case is now, depending on the code word he chooses on the codebook, there are so-called satellites. And now, if he chooses as common message 1, then he chooses the second dedicated message for decoder 1 in the satellite. So that means the code word depends on the center here. So perhaps it's better to see, that's the reason why we called off stacks. So we have stacks codebooks because this codebook is stacked about this and so on. And how it's done, you see better perhaps in this picture here. Let's assume in this circle here are all possible code words in it. Now, if you want to send to code words, we first select the center here. That's the cloud center, which depends only on the common message. That's this one here. Then around this code word, there's a cloud. And in this cloud, we find the code word words. We choose the code words, or we choose these elements just depending what is the dedicated message. So that means if we know that we can receive some code word in this sphere, then we know the center is the common message and the satellites are the dedicated message. That's the idea of superposition coding. Let's look at it in more detail. Again, as I told you before, we assume that R2 is equal 0. And we consider a joint distribution between U, X, Y1, and Y2, such that we can write it as P as the joint distribution of U and X, and the distribution of Y1, Y2 conditional on X. Of course, this is somehow the channel. And the alphabet of U is denoted by this U again. So the code construct for the code construction, we first consider this distribution, joint distribution of u and x, and we generate 2 to the n R0 code words un of w0. These are the code words for the common message. And we use there the distribution pu and make the codebook for that. Next, for every code word here of a common message, we generate 2 to the n R1 code word x of n of w0 and w1 by choosing the symbols xi of w0 and w1 independently at random according to the distribution px under the condition u. And this second step is called superposition coding. So somehow these are the satellites in our picture. So this is the center and these are the satellites. So in the space of all code works, we can view un of w0 as a cloud center and xn of w0 and w1 as the satellite. Now the encoder, given w0 and w1, he transmit xn of w0 and w1. Now decoder 1, he gets y1 to the n. He tries to find now a pair w0 tilde and w1 tilde such that un of w0 tilde, xn of w0 tilde, w1 tilde, and y to the n are jointly typical concerning u, x, and y1. If there is one or more such pair, then choose one and call it w hat of 1 and w hat of w1. Sorry, w hat 0 of 1 and w hat of w1. So this is the estimate of the common message, and this is the estimated of the dedicated message. If there's no such pair, then we put out 1, 1. Now the decoder 2, because R2 is 0, only want to get the common message, so he get y2 to the n, and he tried to find now a w0 such that un of w0 tilde and y2 to the n is jointly typical concerning u, the joint distribution of u and y2. And again, if there is one or more index, choose one, and otherwise just put out 1. That's the construction. This is called superposition coding. And this method was introduced by Martin, and she used it to show a rate region for the general broadcast channel if R2 is not equal 0. So she have to combine it also by binning. So we will come to this later. Just look now at our special case. Now let's do the analysis for this special case. So very simple is it for decoder 2. We have, of course, that un of w0, xn of w0 and w1, y1 to the n, y2 to the n is jointly typical concerning u, x, y1, and y2 have probability 1, or it goes to 1 for very large n. That's already we proved and we know this. And if we just now consider decoder 2, that the probability that this decoder finds a correct finds an incorrect w0 tilde can be made small if r0 is not too big, and if it have to be smaller, like we showed before in the case of the mutual information of u and y2. I think that's the easiest case. Then we look at the first decoder. In the first decoder now we have to look at several cases. The first case is that the estimate of the common message is wrong, but the estimate of the dedicated message is correct. Second is the estimate of the common message is correct, but the estimate of the dedicated message is wrong. And finally, both are wrong. Let's look at the first case. So that means we look at the probability that un and xn and y1 to the n are not jointly typical. So, and we have to look at all the unions of w tilde not equal to w0. But we can estimate these probabilities, we can estimate every of these probabilities by 2 to the n to the minus the mutual information of ux and y1. That's exactly what is written here. So that's the estimation of the probability here. And we assume all have the same probability, and by union bound we can assume that all have the same probability, and we can sum up them. And then we look how many elements we have in the sum. We have exactly 2 to the n 0 elements here. So in putting this together, we get here that this is lesser equal than 2 to the n 0 minus the mutual information of ux and y1 plus 2 epsilon, the entropy of u of x, where this goes, of course, to 0. Now let's look at the second event. You should be used now how we prove this. So again, we looked now at the second event. That means the cloud center was, the estimate of the cloud center was correct, but the estimation of the satellite was wrong. So that means that this part is not typical under the condition that un is equal un. That means we have to take the union over all w tilde 1 which are not equal to w1. In total here, of course, we have 2 to the n r1 elements here. And again, we do that, we estimate this set here by always the same probability. And because of the union bound, we can write it as a sum over all of them. And here we have then the probability of this is 2 to the minus the mutual information between x and y1 under the condition u, and this term which goes to 0. And if we estimate this, again, we look here, this is a cardinality, this is so many probabilities we have, or so many elements in the sum we have, and this is the estimation of each probability here. And so we get this condition here. So the last one is that neither the center is correct nor the satellite is correct. So we have to take the union over all w0 not equal w0 and the union over all w1 tilde not equal w1. That these are jointly, these are jointly typical. So again, we look at the probability here and estimate this all with the same probability here. And then we can write this as a sum and look how many elements we have. We have exactly 2 to the n r0 plus r1 elements, and we can estimate this in this way. So that's the third condition. So we have these 3 conditions which we have to fulfill. And taking this together, then we get the following result. So we have that R0, R1, and 0 is the capacity, is an achievable rate if it holds. 0 is lesser equal, R0 is lesser equal to the mutual information between U and Y2. 0 is lesser equal, R1 is lesser equal to the mutual information between X, Y1 under the condition U. And the sum of R0 plus R1 is lesser equal to the mutual information of X and Y1, where Ux and the joint distribution of Y1 and Y2 forms the Markov chain. So this is a little bit modification of the original way it's done, but it's a little bit easier. This is due to Bergmans, and is based on the work by Kova. I think it's also in Kova's well-known book. You can find this construction, also the Bergmans one. And it turns out that this U can be made smaller than y plus 1. So the cardinality of u can be restricted. But we never talked about the way we do this, so it's just a remark here. Moreover, it turns out that this here is also the capacity if R2 is equal 0. And now to speak about the case where R2 is greater 0, I remind you on our survey, of course, we can use some bits of the common message just for the dedicated message of R2. So we can just take here 1 minus alpha times R2 and alpha times R0 and alpha times R2, like we have in the property I described you in the survey. And then we get a resulting region R0, R1, R2. That's very simple. So we just replace R0 by I0 plus R2 somehow. Yes, that's the way I described it by alpha. And in this way, we get a rate region, in this case, also with R2. So we get a first simple estimate by superposition coding for the rate region of the broadcast channel.